Hi, I'm Swamrath, and welcome to my channel, Unraveling Science. Though we normally attribute science to the large phenomena, today let's unravel some of the smallest yet most important components of our universe: atoms, molecules, and bonds. But before we can do that, let's first take a look at a chart that many consider to be the basis of chemistry, the periodic table of elements. Now, depending on what shows you watched as a kid, you may have a very different idea of what elements are. I mean, for me personally, for a long time, I thought that elements were fire, lightning, earth, and ice. Yes, I watched a lot of Ninjago as a kid. And if you watched a lot of Avatar as a kid, you may have thought that the elements were earth, fire, water, and air. Well, regardless of what shows you watched as a kid, that's not the point. But what I'm trying to tell you is that for the purpose of science, none of those are considered elements, and the elements are actually the 118 listed on the periodic table shown right here. So why are these 118 elements considered elements and not things like water, earth, fire, ice, lightning, you name it? Well, that's because an element is simply a substance that cannot be broken down any further by chemical reactions. So here we have hydrogen and oxygen, which are both elements since they cannot be broken down any further by chemical reactions. However, water, if it was to be subject to a specific chemical reaction, it could be broken down into its two components, which are hydrogen and oxygen. So, what do elements have anything to do with the three small components that I mentioned earlier: atoms, molecules, and bonds? Well, an element's properties are dependent on the structure of the atoms that make up the element. So, what exactly is an atom, you may be wondering now? Well, an atom is simply a small unit of matter that's composed of subatomic particles called protons, neutrons, and electrons. So I'll explain what each of those three are. Let's start off with protons, which are located in the nucleus or center of an atom. They're in red right over here. Protons are one astronomical unit in size, which is very, very small. And as you may be able to deduce from the plus on these protons, they are positively charged. Next, we have neutrons, which are also one astronomical unit in size. So protons and neutrons are the same size. And they're also located in the nucleus of the atom along with protons. They are neutrally charged, just like their name says, neutron, neutrally charged. And third, we have electrons. So electrons are not located in the nucleus of an atom, as you can see right here. They're located on these rings that surround the nucleus, which are called electron shells. Electrons are extremely small, like very, 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 very small. And they're so small, in fact, that when calculating the total mass of an atom, called the atomic mass, we don't even consider the size of the electron. So that's how small they are. Furthermore, another important thing about electrons is that they are negatively charged, as shown by the negative sign on the electrons in this diagram. Because they're negatively charged, and most atoms are neutrally charged, they have a net neutral charge, there's normally the same number of electrons and protons in an atom. So for example, hydrogen has one proton, so that's positively charged. So it also has one electron to cancel out that positive charge, so it's net neutral. So to sum what I just said up, protons are positively charged. You can remember that by thinking proton P, positive P. Neutrons are neutrally charged, neutron, neutral, similar words. And then finally, electrons are negatively charged. So now let's use this new information about the structure of atoms and connect it to our handy periodic table of elements. Well, elements are composed of one type of atom that has a unique number of protons, neutrons, and electrons. So for example, lithium has 3 protons, 4 neutrons, and 3 electrons, while iodine, which is right here, has 53 protons, 74 neutrons, and 53 electrons. Wait a minute. I said that lithium has 3 protons and the number 3 is written on the top left corner. And I said that iodine has 53 protons, and the number 53 is written on the top left corner. No, this is not a coincidence. This is actually meant to be, as uh, the number on the top left corner, sometimes it's written directly above the symbol right here, is called the atomic number of the element and is unique to each element. No other element other than iodine has an atomic number of 53. So what exactly does the atomic number represent? Well, it represents the number of protons that an element has. So iodine, like I said, has 53 protons, as denoted by the atomic number right here. But the atomic number also tells us the number of electrons because iodine also has 53 electrons. And that's because, as I mentioned when we were talking about the structure of an atom, the number of electrons and protons in an atom are, for the most part, the same because electrons are negatively charged and protons are positively charged. So in order to cancel out their charges and make the atom neutrally charged, the number of protons and electrons have to be the same. Therefore, for the most part, there are some exceptions to this rule. The atomic number tells us the number of protons and electrons. Now, the periodic table also gives us the number of neutrons in an element, but it's not as obvious. See this decimal right over here? That is called the atomic mass of an atom. And it's basically telling us the sum of the neutrons and protons in an atom. That's because a neutron's mass is 1 astronomical unit, and a proton's mass is also 1 astronomical unit. They're the same size. So therefore, all we have to do to find the number of neutrons in an atom or an element is subtract the number of protons, 53 in iodine, for example, from the atomic mass. So we round this 127 minus 53, and that would be 74 neutrons. So that's how you'd find the number of neutrons. You just use the atomic mass, the atomic number, subtract them, and boom, you get the number of neutrons. So let's practice with that. So carbon, we're going to use that for our example. Carbon has an atomic number of 6, and it has an atomic mass of 12. How many protons, electrons, and neutrons does it have? I'll give you a few seconds, and you can also pause the video if you need more time. Well, if you said that carbon has 6 protons, 6 electrons, and 6 neutrons, you're absolutely correct, and great job. If you struggle to get that, then watch over the last few parts of the video a few more times, and it's not that difficult a concept once you get the hang of it. Now, you may need to know about isotopes for your science class. Well, think about isotopes as just variants of each element that have a different number of neutrons and thus a different atomic mass. Well, let's take carbon, for example. Carbon has 3 naturally occurring isotopes, and these are carbon-12, carbon-13, and carbon-14. Carbon-12 has 6 protons and 6 neutrons, and it makes up 99% of all the carbon in the universe. Since it's so much more common than the rest of the isotopes, we generally consider carbon to have 6 neutrons, just like it does in carbon-12. The next isotope is carbon-13, which has 6 protons and 7 neutrons. Notice how the proton number doesn't change, although the neutron number increases. And that's because if the proton number were to increase or decrease, if it were to change at all, the element would not be carbon anymore. For example, if the proton number were to increase to 7 from 6, carbon-13 would then be a nitrogen atom rather than a carbon atom. The final type of isotope is carbon-14, and it has 8 neutrons and 6 protons, giving it an atomic mass of 14, as denoted by its name. Sometimes what happens when there are too many neutrons and protons in the nucleus of an atom is that the atom becomes radioactive, and that's the case for carbon-14. It's radioactive. Radioactive atoms shed their radioactivity periodically in a process called radioactive decay. Radioactive decay makes radioactive atoms really easy to track, making them really useful in many medical applications, such as imaging and tracing. So hopefully that gave you a firm understanding of atoms and elements. In the next part, we'll discuss what happens when different atoms interact. Thank you for watching and hope you learned a lot.